Hiya! So in this video, we're going to keep going on about this exact one form idea. So a quick recap of what exact one forms are. So remember what we did is we started off with a differential zero form. We took the derivatives, all the partial derivatives, and that gave us a one form. And we said generally when this is what happens, we're going to call this exact. So if a one form is equal to the partial derivative, sorry, not the partial derivative, is equal to the differential of a zero form, then we're going to call it exact. Today, what we're going to first look at is a way to see whether this is true or not. Like how do I know this is okay? So proposition 2.26, what we're going to have is that we're going to start off with some omega. So here we have an omega, which is a one form. So I don't know what it is. It's some one form. If W is exact, then what we're going to have is that the following is true, right? So if it's exact, then we get this, but note that the opposite is true. So if we have this, it's not necessarily exact. So let us see how this works. So we're going to do a quick proof. So what's this thing I put in box? Actually, I should mention this. Basically, what we do is we take the partial derivative of any of these components. So here we'll take some gi. And we want to compare it to some partial derivative from some other component, and they should commute, right? So I should be able to, in essence, take the partial derivative, go to I, partial derivative, go to j, and then I should be able to go back. So I should be able to go to j, and then j, I should go to I and land in the same spot. So that's the idea here that we're trying to figure out, and that's what this equality is telling us. So let's see how this works. So a quick little proof. In essence, we're going to have W is exact if and only if there's some function f where omega is equal to df, right? So this is precisely what we had said. In other words, this is saying that our gi is precisely of the form partial of f over partial of xi. This is what this definition, this equality here is telling us. So this gives us this. Now, we should be able to differentiate with respect to any of the other x's. And remember, this should commute. So in other words, if I start off with here and I I do another partial derivative with respect to something else, I can now split this up. So gi, remember, is coming from here. So in other words, I can split this into two. Now here I can commute. So I can change these two. So xi and j switch. And now I kind of go backwards and I see that this is giving me the exact thing. So we can show something like this is true. So this proposition is useful for trying to rule out whether one form is exact, but it's not necessarily true that the converse is true. So let's kind of look at this. Let's kind of see how this is useful for us. So let's look at an example 2.27. And basically what we have is we're going to look at this one form and we're going to show it's not exact. Or in other words, when is it potentially exact? So first, when is it non-exact? When is it not exact? So here, remember, we have to take the partial derivatives and kind of see how it is. So here, what we'll do is we'll take the partial derivative of omega. I guess we'll start off with the x component. So we'll start off with here. So here we'll do of lambda y of dx, right? No, we want the other one because we're already in x. So we want y. Yep. Now the derivative here should be lambda. And now the opposite side, what do we have? We have dx over dx because we have the x here. I should do a different color so we can kind of see which one it is. And then dx. So we want this dx with x and then this lambda y with the dy. And so here, if I do the partial of x divided by the partial of x, this is just going to give me 1. So this is not exact if lambda not equal to 1. Okay, so when is this exact? So when is omega exact? So now the question is omega, I guess, rewind. So now the question is omega exact when lambda equals 1. And it turns out we can actually, this is true. And the way to look at this is we start off with our coefficients here. So we take y dx. This gives me xy plus some factor in x. If I do the opposite, the other one, this is going to give me xy plus cy. So in other words, if I look at this function here, if I let f be xy, this is going to give me the derivative, the exact partial derivatives I want. So this f xy gives me that omega is equal to df. So why did I kind of do this? I'm going to break this down actually a little further, even though this is going to make the video longer, because I think here when I did the integrals, it might be like, wait, why the fudge did you do these integrals? So basically what I'm trying to do is, since I know that I want to take the derivatives of some function to get these components, right? Because exact is basically saying that these components here, these have to come up from some df, and I want to take some derivative of something, right? So either x or y. So in other words, this is going to come from some function and I want to take derivatives. So in other words, since I already know, since I'm assuming these are the derivatives of something, I need to be able to go back up in order to find what the things are. So in other words, I need to take the integrals in order to be able to figure out what this function might have been. And so that's why I did the integrals. So as a remark, before we end this section, is that the purpose of differentiating a function is to just give a linear approximation of it at that point. So with exact forms, we can now give some like geometric intuition as to what this is happening. So if we look at this f function from before, so we took this f function. Remember, this was that like weird curve thing. It looked like I don't know. I can't even draw it very well. Anyway, it's like this weird curve ball thing, right, in like 3 dimensions, etc. I'm not even gonna try. Anyway, you know what I'm trying to draw, like the picture from above. Actually, it might be faster for me to just go to the picture. There we go. This shape thing here. So we're gonna look at this shape, and basically remember that we had the differential for this, and when we looked at this, what we saw, oops, went too far. We had that the differential for this is given by this function. And it's going to assign, so if we take it to some point p11, what this is going to give us is v is going to be sent to vx plus vy. So this is a fun little exercise if you want to try this. We already did something similar to this with a 2 here. But here we're just doing it with a 1, so figure out where this came from. And basically this is showing this level sets on the linear functionals. So this is basically seeing this, and how, so another way that we can consider these level sets of f around the p is that we can compare the differential applied to this p. So in other words, we take this omega, right? So this is our one form, and we apply it to this point p. This is going to give us a linear approximation of f at p. So this is in essence the purpose of differentiating. In other words, with this intuition, we can kind of think of these as these exact one forms as encoding linear approximations of f at every single point p. So in other words, these one forms are pretty strong, right? It's giving us a lot of information for almost nothing. So if a one form is not exact, then it can still encode many linear approximations, but in other words, there's just no zero form f that can be approximated in this way. So in other words, there's not like some function that this is approximating precisely, but it could be doing many different linear approximations in some other way. So yeah, so we will leave it. Oh, here we actually have the kind of things. So here you can kind of see the linear approximations at the points kind of on this line, and you can kind of see that these are just the tangent lines, right? So these lines here are precisely the tangent lines at these curves kind of things. And the linear functionals are precisely this. So yeah, so I'll leave this here. In the next video, we're going to now look at one forms and we're going to apply them to vector fields, right? Because these one forms, remember, they're functions. So we're going to apply them to a vector field and see what these functions do to vectors. So I will see you in the next video. Peace.